Hello there, everyone. I wanted to create a video to help you review the advanced bonding topics that we talked about today in lecture. So I'm going to review the ideas of the orbital overlap in covalent bonds and then go over the hybridization theory that we talked about so that you can have some additional practice with this as needed. So we first talked about how orbitals overlap in our covalent bonds. And the idea was that we were trying to create a slightly more sophisticated model for how these covalent bonds form. So up to this point, if we looked at a hydrogen bond and an H2 molecule, all we've done is just use the valence electrons using our dot symbols and our Lewis structures to show how these electrons are shared in these bonds. So we just use these paired electrons or these dots and our dot symbols to show the bond. Well, we want to begin thinking about these bonds in a little bit more sophisticated manner. So if we think about hydrogen, we know that hydrogen will involve a 1s orbital. So if we draw two hydrogens, each with the 1s orbital, and of course we know that we'll have these unpaired electrons in each hydrogen, and these orbitals are going to overlap, and this is what's going to allow our bond to form. So it's overlapping 1s orbitals in this hydrogen molecule that allows the electrons to pair up. And now this electron density becomes distributed throughout the molecule. So if we look at a fluorine molecule, so if we look at the Lewis structure for F2, again, we'd see something like this where we just use the two electrons or these two dots in our dot symbols to represent that's the electron density that's being shared. Well, if we look at two fluorine atoms, of course we know that we have 2s and 2p orbitals that comprise our valence orbitals. And if we draw in our electrons, we can see hopefully that in the F2 molecule, the two orbitals that are likely to overlap are these 2p orbitals, because they're the two orbitals that contain the unpaired electrons that could then pair up to form our bond. So the 2s orbitals we can see are full, so these orbitals are not likely to mix. And of course these other 2p orbitals are unlikely to mix as well because they're also fully occupied. So these are going to be the electrons that comprise our non-bonding electrons in a Lewis structure. And if we draw this fluorine molecule using these 2p orbitals, right? So if we take these two unpaired electrons, now we can imagine that each fluorine would have now these unpaired electrons overlapping from these 2p orbitals to form our chemical bond or our shared electron bond. All right, so then in lecture we did the example where we looked at OH in water, the OH bond in water, and we came up with a similar result, but now because water has unpaired electrons in the p orbitals, and of course hydrogen has unpaired electrons in its 1s orbitals, then we're going to have a 1s 2p mixing in our OH bond. So the s orbital from hydrogen is going to be mixing with the 2p orbital from oxygen. So if we kind of draw that, so we have oxygen And let's draw one of the p orbitals in that direction and another one of the p orbitals in that direction. We put in our unpaired electrons, and then we have hydrogen with its 1s orbitals. And now these are going to be our bonding sites, so the 1s 2p orbital overlap. So you can use this orbital overlap using these valence electrons to predict fairly simple molecules. So for instance, we were able to predict hydrogen, H2, fluorine, F2, water works pretty nicely. However, what we find with BH3 and CH4 is we get molecules from our Lewis structures that are not quite what we would predict. So we have, of course, with BH3, we have an electron deficient molecule that doesn't follow the octet rule. And CH4 is something that we get that's not predicted by the valence electron configurations. And so we need this other bonding theory to explain how these molecules work. And this is where we use this hybridization theory to explain these two molecules. So when we did the problem in class, we stated that if we use our valence theory, so carbon, of course, has a 2s and 2p valence orbitals, and carbon has just the two unpaired electrons, we would predict that we could form two bonds with hydrogen, because each hydrogen has an unpaired electron. So in class, you should have predicted that CH2 is the molecule we'd predict using this valence orbital theory. However, as most of you selected, in reality that CH4 is actually one of the more commonly observed molecules in which bonds form between carbon and hydrogen. And so the question is, well, how can we get CH4 if we're only predicting two bonds forming with hydrogen based on this valence electron configuration? And so, of course, we're going to use hybridization. So this is the valence electron configuration. You would expect a molecule something like CH2 to form if that were the configuration. However, we know that if we have CH4, we must have 4 bonds. And so perhaps somehow one of these electrons from the s orbital moves up, giving us 4 unpaired electrons. So that would give us 4 CH bonds. However, we would expect one of these bonds to have a shorter bond distance. So the CH bond that forms here, you would expect a shorter CH bond distance to form because s orbitals are slightly closer to the nucleus. And so you would get a shorter distance between the hydrogen and the carbon. So it turns out that when we structurally characterize methane, that we get 4 equivalent bonds, all equal distances between a carbon and hydrogen. So we have to modify this further. And so the only way to get 4 equivalent bonds between carbon and hydrogen is to now somehow take these valence orbitals and they're going to hybridize. So this is our hybridization. That just means mixing. And now if we take those 4 orbitals and we get 4 new equivalent orbitals, which we call sp3 hybrids, now we can have 4 sites at which we can bond hydrogen atoms. Okay. So again, as I mentioned in lecture, you don't want to think about carbon doing this first on its own and then forming bonds. So what happens is if we take carbon atoms and hydrogen atoms and we react them together, in the process of the chemical reaction, this hybridization is going to take place, and the type of hybridization you'll get will depend on the reaction conditions and the stoichiometry, or the ratios of hydrogen and carbon that we're mixing together. So even though we're kind of creating this model that seems like it's happening in a discrete way, try and remember that this would kind of be happening during the course of the reaction. All right, so if we take these sp3 hybrids, I tried to show you the shapes of these hybrids. And so if we take, let me use red. So if we take an s orbital and we mix it with a p orbital, then we get a new hybrid orbital where the in-phase components, so the unshaded components of the orbitals, mix and become amplified, because now we're having constructive interference. And then you have this smaller lobe that represents the out-of-phase portion of the p orbital. So if you take this, so now we form 4 of these on carbon, and now we're going to overlap them and place them on the carbon atom. So that's what this picture is trying to show, is the 4 sp3 hybrids that are residing and sitting around carbon. Well, if you have 4 orbitals, each with an electron, so these little dots represent electrons, that's going to give you a tetrahedral geometry. So sp3 hybrids always form tetrahedral geometries because you have 4 electron densities sitting around the carbon atom. Now you can see how each hydrogen in its 1s orbital with its unpaired electron, how each hydrogen can form now bonds with these hybrid orbitals, and now we get this methane molecule, 4 equivalent CH bonds, tetrahedral geometry, each of which has a pair of electrons in a covalent bond. So we're just using this hybridization model to try and explain a new experimental observation that we've made that Lewis structures can't explain. So when you get to organic chemistry, of course, you're going to be working with molecules that are dealing with carbon atoms, and so the bonding of carbon is going to be extremely important when you get to organic chemistry, or Chem 8, Chem 8A. And so I want to just introduce you to this topic now. So that's your sp3 hybridization. As we mentioned in class, we can also have sp2, and this is where I showed you the visualization program, so you can copy that link and we can go view the visualizer. So here's the Lewis structure for this is for ethene. So we have a double bond between the carbons. Each carbon is trigonal planar. So we no longer have an sp3 hybridized molecule, we have an sp2. So what we do is we take, now we have an s orbital plus 2 of the 2p orbitals, and we get 3 sp2 hybrids. So now the shapes of these hybrids are similar, so the hybrids still look like a large unshaded phase with a smaller region, and now we place these around the carbon in a trigonal planar fashion. So now we have 3 of these hybrids, so the shapes look similar, but there are only 3 of them. And now we then have an hybridized p orbitals. So we only use 2 of the p orbitals, but we have 3 total p orbitals. So then we have this unhybridized p orbital that sits perpendicular to our trigonal planar hybrids. And so that's what I was trying to show you with this visualizer. So here you can see the ethene molecule with the double bond. I'm going to show you now the sp2 hybrids. So these are the 3 sp2 hybrids that sit on one of the carbons. So you can see they have kind of the similar shape that we've talked about, trigonal planar geometry. Now I'm going to show you the sp2 hybrids on both carbons, and you can see we form this first part of the bond. We call this a sigma bond, that where the sp2 hybrids interact head to head. So this is called a sigma bond. So this is where the sp2 hybrids interact head to head. And then I showed you the sigma bond plus the unhybridized p orbital. So you can see here the yellow p orbitals that are perpendicular, which you can see here in this cartoon are blue and red on the PowerPoint. And then if we now mix those 2 unhybridized p orbitals, that's where we now form the pi bond that I talked about. So this is the double bond. So the head-to-head interaction is the sigma. That's the first part of the bond. This side-to-side interaction is the pi bond. So that's what we call a pi bond, which you can see here. So pi bond means you're getting a side-to-side overlap between those unhybridized p orbitals. So sigma means head-to-head. That's with your sp2 hybrids. Pi bond means side-to-side. And that's with the p orbital that's unhybridized. And so notice the first part of the bond has 2 electrons, and the pi bond also has 2 electrons. So even though the pi bond looks like it's in 2 different places, this is technically one lobe of electron density that has just the 2 electrons in it, which you can hopefully see here on the visualizer. Okay, so hopefully that gives you a good review of what we did in class. So sp2 hybrids are similar to sp3, but now we have 1 fewer p orbital involved. Now we get a trigonal planar geometry. So now we can just simply use the geometries. So sp3 hybrids are always tetrahedral. You can see the sp3 hybrids here in purple on this cartoon, and molecules with tetrahedral geometries, those are going to have sp3 hybridization. sp2 hybridization gives us the trigonal planar geometry, which you can see here, and bf3, bh3, which we just saw a moment ago, has sp2 hybridization, or this ethene, where each carbon is trigonal planar. Right, so we're with respect to each carbon, we have a trigonal planar geometry. Now there's also sp hybridization. That's where you have a triple bond. So say you have ethylene, that was a molecule you drew in your worksheet in class. This has a linear geometry. So sp hybridization means we have 2 unhybridized p orbitals. That's how we get the triple bond. So you get the head-to-head interaction from your hybrids, and you have 2 sets of p orbitals that can interact to form this triple bond. For the sake of the exam, I just want you to focus on these 2 types of hybridization, sp3 and sp2. If you can understand these 2 types of hybridization, you're going to be in good shape when you get to organic chemistry. sp hybridization will come up, but for now, let's just focus on sp2 and sp3. Okay, so let's go over the questions that we had in class. Because borane, BH3, which is borane, we know that we have a trigonal planar geometry. Sorry. So if it's trigonal planar, it has to be sp2. And hopefully you can imagine that we would have an sp2 hybrid, and then we would have this unhybridized p orbital perpendicular. So this is empty, an empty p orbital. And of course we have our boron with 3 valence electrons. So now the 3 valence electrons from boron spread out into these 3 hybrids. And now you can have hydrogen bonding at each of these hybrid orbitals using its 1s orbital, which is of course spherical. And then we just pair up our electrons from the hydrogens. So hopefully you can see now how this sp2 hybridization is a much better model for explaining the bonding in borane, or BH3, whereas with the valence theory, we would have predict only one bond with boron. And then for the second example, I wanted to draw this molecule. So this was the bonus question at the end of lecture. So that's the Lewis structure for acetic acid. The carbonyl carbon is the carbon that contains the bond with the double bonded oxygen. So the bond with the double bonded oxygen. So hopefully you can see here that carbon, because it's trigonal planar, you have only 3 electron regions around this carbon. This carbon would be sp2 because it's trigonal planar. And then if we look at the other atoms though, this carbon would be sp3. We could see that this carbon has 4 bonds or 4 electron regions, that it's tetrahedral, so it has to be sp3. This oxygen has 4 electron regions, so it's sp3. It's tetrahedral geometry. And this carbon, this oxygen, the carbonyl oxygen, or the double bonded oxygen, has 3 electron regions. So it has a bond with carbon, 2 lone pairs. So this carbon is sp2, and it's trigonal planar. Okay, so hopefully that gives you a good review of what we did today in class in regards to hybridization. So remember, just be able to use the geometries of the atom within a molecule to predict the hybridization. And remember, hybridization only works for second period elements. So carbon, boron, nitrogen, and oxygen. These are essentially the only atoms that are going to have significant hybridization. The reason why elements below these, so for instance, if you go to n equals 3, so if you look at aluminum, silicon, phosphorus, or sulfur, because when you go down to n equals 3, the energy gap between s and p orbitals tends to increase, and so the ability for the s and p orbitals to mix below these elements is not very effective, and so they don't tend to hybridize. So these are really the only elements you have to worry about in terms of hybridization. But it's a very powerful theory, can help us explain the bonding of carbon, which again, we could see using our valence theory is sometimes unpredictable. It helps us explain the bonding of boron, which when we did Lewis structures, we had to say it's essentially an exception to the octet rule, and it's electron deficient, but now hybridization more readily explains that bonding. All right, so hopefully that will help you for the exam. And if you have any further questions, don't hesitate to get in touch. All right, good luck.